But today, I'll be talking on how we can calculate the molecular surface interaction using DFT, and trying to describe the current status and the ongoing challenges we are facing in DFT calculations. So here's an outline of today's talk. In XYG3 is functional developed originally for molecular system, but then we have two ways, PBC and exo-PBC, to extend the application from molecular system to the extend solids. I will explain the method and show their performance later in this talk. So needless to say that DFT has made a tremendous contribution to many fields, including chemistry, materials, and catalysis, and of course, CCST. More than 90% of theoretical calculations are carried out by using DFT method. So literally, DFT is a leading first principle method used everywhere. Of course, as the exact functionals are unknown, so certain approximation have to be adopted in practice. According to the statistics, the functional which is most popular in material science is PBE. So is PBE often run in a program called WASP, whereas the functional that is most popular in chemistry is BIS-RELIP, often run using program called Gaussian. So while BIS-RELIP used to be the #1 choice, here is a recent survey done by DOE. As you can see here, more than 1/3 of application run in their simple computer center are DFT calculations, while most of which are WASP calculations. This, in a way, reflects the growing importance in energy chemistry to achieve the goal of carbon neutrality, as emphasized by the computational chemistry. Well, for catalysis, this is where small molecules meet bulk solid. Reactants in the gas phase are activated through interacting with the surface of catalyst, which transform the reactants to the desired product. Therefore, you need a computational method that is good for both chemistry and the materials. So the former should be able to describe the accurately chemical bonding and breaking and forming, while the latter should be capable of describing the electronic structure of the solids in the surface. So in fact, every surface process is related to a gas phase reaction by chemisoption energy to form this Born half circle. So to this end, a computational catalysis on surface will be less meaningful if the gas phase reaction cannot be suitably described in the first place. So now let's see how well a DFT functional popular for material science, as for the PBE, works for chemistry. So here show two examples. The first one is CO-directed dissociation with PBE at WASP. The CO bond strength is overestimated by 20 kcal/mol in gas phase. Then for the surface reaction to be accurate, we have to rely on idle cancellation by all this amount, but of course on the opposite side for different metals and different facets. So there exist many other reaction possibility to form a complex reaction network. So here say we have CO hydrogenation, which now has an idle of 12 kcal/mol in the gas phase by using PBE WASP. And for then again, for the surface reaction to be accurate to describe, we have to rely on idle cancellation all by this amount on different metals and different facets. So in addition to this quantitative error, we may also encounter qualitative error. For example, this is a CO2 adsorption on platinum 111 surface, where the experimenter observed that the CO adsorbed on the top side of the PT111 surface. PBE suggests that CO would adsorb on the bridge side and the hollow side. So in this agreement with the experiment. So further analysis showed that this is because PBE suffer from a so-called delocalization error. So the exact energy for the fractional charge should be a straight line in interpolation between integer points. But nevertheless, the conventional functionals show convex deviation from the end. So this delocalization error leads the 5 sigma orbital, which is a HOMO of CO, to high lying, and the 2 pi star orbital, which is a LUMO orbital of carbon monoxide, to low lying. So the PB functional will underestimate the sigma donation, which prefer the on top side absorption, and overestimate back donation, leading to the wrong description of the absorption side. And so here are the numbers for the HOMO and LUMO orbitals from PBE, and you can compare this number to the reference. And of course, for BISRIP, it's getting improved, but the improvement is not significant enough. And here's our functional XYG3. The results are in perfect agreement with a reference number. And also, as you can see, that the XYG3 fulfill the linear condition for the fractional charge behavior. Then, what is the XYG3 function? So over years, there are many DFT functional being developed based on different principles, using different ingredients from density to density gradients and the Laplacians. So this is a produced view that groups DFT functional into 5 lines from Hartree world to heaven of chemical accuracy. The PBE functional is a LUN 2 functional developed from solid state molecules, while BISRIP is a LUN 4 functional developed for chemistry of molecules. So today I'll be talking on XYG3, which is a 5th LUN functional developed in our group. It starts from the adiabatic connection formalism and combined with Gaudian-Levy second order perturbation. So most specifically, the Hartree exchange describe the initial position of the adiabatic connection formalism from a non-interacting system to the fully interacting system, while the second order perturbation describe an initial slope, which are both important for an accurate construction of the functional. So XYG3 is actually a double hybrid functional, hybridizing both Hartree exchange, DFT exchange. So formally, the computational scale is increased now because now we explicitly treat all double excitation P2 term. So here shows how the computational times increase with the system size. The scaling for the PT2 is formally n to the 5th power, where n measures the system size. But however, it's only a pair of electrons of opposite spin can make chemical bond. So we may only explicitly treat the opposite spin electrons and leave all the same spin electrons to be described by DFT. In this way, the scaling will be reduced from n to the 5th power to n to the 4th power, and we arrive at the functional called XYGJOS. So, and of course, it's only when a pair of opposite electrons are in close proximity that makes important contribution to the chemical bonding. If they are far away, and then we can leave all this be described by DFT. So with this locality taken into account, and we can actually reduce the scaling further to n to the 3rd power, which is then very similar to conventional DFT for self-consistent SCF calculation. So let's check the accuracy gain by using XYG3 and XYGJOS functional, which collectively we call XDH functional. This is for heat of formation. Which measures how well a functional can do in describing chemical bonds of small molecules. So you can see the result of PB is worse than B-squared, as you may have expected. And in particular, the errors getting increased as the system size is increased. So this is a bad. This is so. This is an XDH functional, which performs satisfactory approaching chemical accuracy as delivered by the GN theory, which is coupled cluster-based being way expensive. So here it shows the functional performance for reaction barrier heights. And so we have examined heavy atom transfer, nucleophilic substitution, unimolecules, and hydrogen transfer. And the results from XDH are very good as compared to the coupled cluster-based method. But here it would be important to emphasize that many functional do not have a uniform accuracy for different type of reaction mechanism, which prevent biased mechanistic study on different pathway. So here is functional performance for non-bonded interaction, which are very important for describing the CO2 capture. So we have examined hydrogen bonding system, charge transfer system, dipole interaction, weak interaction, and papa stacking. So again, the result from XDH are very satisfactory, approaching the QCISDT results. So on the other hand, many functional do not have a uniform accuracy on different type of non-bond interaction, which may prevent unbiased and mechanistic study if different type of non-bond interaction compete with each other for the system of interest, and this is often the case. Last but not least, here we show the functional performance for geometry. The XDH functional display uniform accuracy for covalent bonds, non-bond interaction, and transition state structure, which is very important in order to explore the whole potential energy surface. So in addition to the energy calculation, we have developed analytic gradient so that we can do geometry optimizations and property calculations, and this has been implemented in program like Gaussian and QChem and Pi SCF. So here shows the performance for the calibration of a calculated vibrational frequency and the NMR shading constant. As compared to the CCST result, we can achieve an accuracy less than 20 wave numbers for vibrational frequency. And for the NMR calculations, we can even push the limit to around 1 ppm, where the computational cost is 3 orders smaller than the CCST method. So then the question is, how can we extend the good performance of molecule to extend the system for the XTH function? So XYG3 PBC, and here PBC refers to periodic bound condition. So here are some represented MP2 implementation with PBC, and each has its own merits and demerits. Our implementation was accomplished in FHIMs, which is based on canonical MP2 for all electrons using numeric atom orbitals. So now we are facing new additional challenges. In addition to the end to the false dependence on the base sets, it also scale cubicle with respect to the K-match, because now we have the translation symmetry. While the memory consumption is demanding and relevant network communication is also very intensive. So it's crucial to have a well-performed K-mesh oriented parallelization. So here I selectively show the K-mesh convergence of the periodic condition for diamond and the magnesium oxide. So we can see the results from Roland functional like LDA, PBE, and HSE converge very fast. However, the cohesive energy converge very slowly for MP2, XYG, and XYG3. So we have to do the extrapolation to have well behaved results. And of course, we still need to pay attention to the base set convergence. And here we show the cohesive energy calculated by MP2, B3, XYG3 for diamond and the magnesium. And you see that the effort is worth it. And we can have very good agreement with experimental results. So now I put side by side in this table the mean absolute deviation for 10 cohesive energy predictions, solids, and the hydrogen for 48 small molecules for the description molecules. So as you can see, this true B-strip works pretty well for small molecules, but not so good for the bulk solid. And PBE, on the other hand, works for the solids, but not so good for the molecules. And this is also true for the more advanced functional scan. The cohesive energy of solid system is more improved, but the accuracy for the molecular system is still not good enough. And here's performance for our functional XYG3, which provides equally good performance for both solids and molecules, showing great promise for being used in computational catalysis. So here is an example discussing on the stability of rutile and N-types, which is important materials. So you can see that the PBE predict that the N-types is more stable than rutile, and which is not in accordance with the experiment finding. So in fact, the volume predicted by PBE are also too large for both N-types and rutile compared to the corresponding experiment results. So the ones scan functional leads to very good prediction on the volume, but still overestimate the stability of the N-types. So here is our results for the XYG-OS, which correctly predicts rutile is more stable than N-types, and also the predicted volume are in very good agreement with the experimental results. So here's another example working on the CO adsorption on sodium chloride 101 surface. And so we compare the geometries and the adsorption energy, and you can see that some other functional which works for the adsorption energy is not good for geometry, and some of them are both poor for geometry and adsorption energy. It's only our functional which can predict both good geometries and adsorption energy. And this is for vibrational frequency calculation. We compare to the oxygen down and the carbon down adsorption modes, and it's only our functional which can correctly give the prediction of the frequency shift. So it is true that so the functional is good, but in real application we have to balance the accuracy and the efficiency. So even the MP2 is only practical for medium-sized crystal system. So this also imposed the limitation on the XDH functional for practical use. So as is well known that the QMM is a powerful method that describe active center accurately, while consider the environment effect. So most specifically, this is a Onium-2 scheme developed by Murakuma's group and as implemented in Gaussian for molecular system. Suppose we have a molecule which is too big, so we can only describe it at a low level. But suppose we have an active center, which is going to be described by the high level. Then Onium-2 takes a form by adding the real at low and the moderate high and subtract the moderate low, and to avoid the double counting. So well, we can actually use this methodology, but extend it from molecular system to the periodic system. So we can actually do PBE at WASP. For the whole crystal, and then we can cut out a class model, and we can do the energy difference for the high level and the low level. So take advantage of the local nature of the correlation. So this is an example of how we can do molecular crystal calculation. So we can do PBE calculation. So with WASP, and then we can do the XY23 calculations for the dimers, tetramers, and trimers and tetramers, and then add them together. So in this way, we gain accuracy and efficiency. And this is a set of 23 molecular crystal, and this is comparison to all the other methods in the literature, and you can see that the XY23 and XOPBC can lead a smallest mean absolute deviation, and also the smallest standard deviation, and smallest maximum absolute deviation. So then let's get back to the surface, and as we have emphasized that every surface reaction is related to a gas phase reaction. In the first place, we need to calculate the gas phase reaction accurately. But now you can see PBE will have larger errors, and often of the opposite sign. And this is bad indication, and XYG3 can have very good description of the gas phase reaction pushing the limit to 1 kilocalorie per mole, often to achieve the chemical accuracy of 1 kilocalorie per mole. And then how about the chemsorption bond? So this is an example for calculating the absorption energy on the copper surface. We can actually, as usual, do the classical calculation with PPE, and then take advantage of the local nature of the chemsorption bond. We can cut out a cluster and do the XYG3 calculation. So in this way, we can improve the accuracy of absorption energy calculation. So here some more comparison. So on the copper surface, there's also a problem, the preference on the top side and the bridge side. So PPE and PPE plus C all get this wrong, and it's only the new functional that we can have a good results in agreement with the reference number. And so one thing I should emphasize is last year Campbell did the measurements on the former absorption, as the CO2 hydrogenation will lead to format, which is often important intermediates on the surface. That what Campbell found is for the PPE functional, the deviation can be as large as 0.7 electron volt, and so making doubts on all the calculations on this surface. And so this is this is CO2 RR calculation results to CO on the copper surface, and you can see that the experimental onset potential on copper 1,1 surface is around 0.6, and this is our calculation value, and experiment equilibrium potential on copper 1,1 surface is around 0.3, and also for the equilibrium potential, the experiment value should be 0.1, and immediately you can see the potential energy curves calculated by PPE and the PPE plus D are dramatically different from what we have, and also differ from experiment results. And this difference is not only quantitative, but also qualitative, because this will predict the wrong rate determined step. So also we can apply the XDH XO PBC calculation to calculate the absorption energy of small alkanes in zeolite, and we believe this kind of methods can also have very good results when applied to describe the CO2 absorption on different materials. So here's some concluding remarks. We have shown you we have developed a good functional for the description, accurate distribution of molecular system, and also for the solids and on the surface. And so this is a paper published a few days ago. So emphasize the central role of density functional theory in the age of AI. So emphasizing that now the machine learning model is heavily depends on the DFT calculation for the data generation. That the data is often at the GGA level. So also I will show you two papers a few years ago. This is a natural cover paper which says we are now seeing a real convergence of what the experiment want is what the students can believe. But there's also a warning message. The truth is, some errors come with the theory itself. You can never be able to correct them. So this is a new editorial published last in May this year, and saying that the chemist, that the AI revolution is yet to happen. So it's only the machine learning system can get accurate and accessible training data, and they won't achieve their full potential. So until then, it could be a high over hope. So uh, I couldn't stop without thanking my group members and collaborators, in particular Professor Yibo Zhang and Dr. Chen Zheng and Dr. Hu Zheng. And with that, also thank you for your